Dear students, welcome back once again to the another session of Econometric Methods course. We had so far seen the estimation and interpretation of regression models. But the interpretation of the model is contingent on the satisfaction of certain assumptions on random error terms. When those assumptions are violated, it has consequences for the interpretation of the model. We are going to discuss about those issues or problems in the forthcoming modules. Firstly, module 21 and 22 would discuss about the autocorrelation problem. The module 23 and 24 would discuss about the heteroscedasticity problem, and module 25 and 26 would discuss about the multicollinearity problem. In each of these modules, I am going to cover the topics relating to the meaning, consequences, sources, tests, and remedies for the problem. In this module and the module that follows it, I am going to discuss about the meaning, consequences, sources, tests, and remedies for the autocorrelation problem. Now let us see the meaning of autocorrelation problem. Let us take the simple linear regression model yi is equal to alpha plus beta x plus ui. An important OLS assumption is expectation of ui uj equal to 0 for every I not equal to j. The same can be written for the time series context, time series models, as expectation of ut minus k is equal to 0 for every k not equal to 0. Now, if this assumption is violated, that is, if expectation of ut minus k not equal to 0, every k not equal to 0, the situation is known as the presence of autocorrelation problem. To understand the autocorrelation problem, let us understand the idea of lag and lead variables. The ut in the time series model is taken as the level variable. The ut minus 1, ut minus 2, etc., ut minus k is denoted as the lag variables, and ut plus 1, ut plus 2, etc., ut plus k is taken as the lead variables. How these variables are constructed, how these variables are derived from one another, we are going to see next. Now let us consider this table. The first column is time and the second column is ut, the level variable. We may derive the lag variables ut minus 1, ut minus 2, ut minus 3, ut minus 4 and ut minus 5 from the level variable. The ut minus 1 is nothing but the value of ut in the year preceding. That means the ut minus 1 is the preceding value of this year. What is the preceding value? This is time 2. The preceding value of this period is 3. The value of the preceding value at ut is 3. So this is the second period value. The third period value is the preceding value again, 6. This is fourth period preceding value, 9. Like that, you can derive the values. Similarly, ut minus 2 is derived from the 2 values preceding to this time. This is 2 period preceding to this is 1 and that value is 3. So you derive the values for the ut minus 2 like this. Similarly, you can derive the ut minus 3, ut minus 4 and ut minus 5. The lead variables are taken as the succeeding values. That is, ut plus 1 is the 6, ut plus 2 is the 9. Like that, it goes. So the lag and lead variables can be specified using the level variable. Now the correlation is in fact defined within these variables. You may derive you may define the correlation between ut and ut minus 1. You may define correlation between ut and ut minus 2. You may define the correlation between ut and ut minus 3, like that. It may go on. We are going to take the simplest of the autocorrelation structure, that is, the autocorrelation between ut and ut minus 1 alone. That can be represented in the regression equation of this form: ut equal to rho ut minus 1 plus Vt. This is the simplest autocorrelation structure. We call it the first order autocorrelation because the lag at time between ut and ut minus 1 is 1. If you define the autocorrelation between ut and ut minus 2, that is called a second order autocorrelation structure. Now let us take the first order autocorrelation structure defined as ut is equal to rho ut minus 1 plus Vt. Vt is a regular, well-behaving stochastic error term. We call it white noise error term that follows all the OLS assumptions. That is, expectation of Vt is equal to 0, expectation of Vt square is equal to sigma V square, that is a constant. Expectation of ut minus 1 is equal to 0 for every I not equal to j. Okay, with this specification, we may derive the value of ut with the time infinity. Ut is equal to rho ut minus 1 plus Vt. Similarly, that can be written for ut minus 1 as well. That is, ut minus 1 is equal to rho ut minus 2 plus Vt minus 1. Similarly, we can write ut minus 2 that is equal to rho ut minus 3 plus Vt minus 2. We may substitute all this value back into this loop. We may get ut is equal to rho into rho ut minus 2 plus Vt minus 1, because ut minus 1 is nothing but rho ut minus 2 plus Vt minus 1. We are just substituting that plus Vt. Right? We may reduce this. You may multiply this rho inside. You get rho squared ut minus 2 plus rho into u Vt minus 1 plus Vt. We may continue this process. Now ut is equal to rho square into instead of ut minus 2, we may substitute rho into ut minus 3 plus Vt minus 2 from the equations before. So this can be reduced, and that will lead to a rho cube ut minus 3 plus rho square Vt minus 2 plus rho Vt minus 1 plus Vt. This may be rearranged, and we may continue this process for infinitum. We get ut is equal to Vt plus rho Vt minus 1 plus rho square Vt minus 2 plus etc. It goes to the infinity. So these expressions may be expressed in terms of the sigma, that is ut is equal to sigma r varies from 0 to infinity rho power r Vt minus r. Now we may derive the properties of ut with the first order autocorrelation structure. Now ut is equal to expectation of sigma r varies from 0 to infinity rho power r Vt minus r. Vt minus r is the only stochastic term, so we may take expectation only for that. So this leads to r varies from 0 to infinity rho power r, expectation of Vt minus r is equal to 0, because the expectation of Vt is equal to 0 for every t. That is the assumption we first made for the autocorrelation structure. Now it means expectation of ut is equal to 0 for every t. We may now derive the covariance of ut and ut minus 1. So that is equal to sigma r varies from 0 to infinity rho power r Vt minus r. Similarly, we may derive rho power r Vt minus 1 r. So we may multiply this and this can be derived, and we can finally end up in this result: rho by 1 minus r square, rho square sigma v square. We are going to find sigma u square is nothing but sigma v square by 1 minus rho square, because here sigma u square is the variance of u and sigma v square is the variance of v. So this may be reduced to rho into sigma u square. In fact, this will help you to generalize the results. Now we can find the covariance between ut and ut minus k. That is equal to rho power k by 1 minus rho square sigma v square, that is otherwise written as rho power k into sigma u square. Right? Well, actually I am in fact but now I am going to derive the variance of sigma, variance of u. That is sigma u square is equal to expectation of ut square, that is equal to, so we get the derivation and we end up as sigma u square is equal to sigma v square by 1 minus rho square, because in the derivation rho square is between 0 and 1. Now let us see some of the consequences of autocorrelation problem. In an SLRM, let us take beta hat is equal to beta plus sigma wt ut, and if we take expectation both sides, we get expectation of beta hat is equal to expectation of beta plus sigma wt ut. Here only this ut is a stochastic variable, and so we may take this expectation so only for that particular variable, and this will lead to beta, because expectation of ut is equal to 0 for every t. That is what we see in the earlier thing. Now, so expectation of beta hat is equal to beta, and so OLS estimators are unbiased in the presence of autocorrelation problem. Now we can say beta hat minus beta is equal to wt ut, and we can find the variance of beta hat as this is a usual derivation. Now we can get the variance of beta hat as, we may derive the variance of beta hat as sigma u square into 1 by sigma xt square plus 2 into double sigma k not equal to 0 xt minus k divided by sigma xt square and sigma u square and rho power k. So we have got two terms. First term is sigma u square 1 by sigma xt square, plus the second term 2 into double sigma k not equal to 0 xt minus k divided by sigma xt square into rho k into sigma u square. So beta hat is equal to sigma u square by sigma xt square when rho equal to 0. So this formula where a variance of beta hat is as sigma u square by sigma xt square underestimates the variance of beta hat because it leaves out the second term completely. So if rho is taken as greater than 0, because that is the most in case true for the economic variables, this second term is strictly positive. Even otherwise, if rho is less than 0, then that the term in fact this will bias the estimate of variance of beta hat. So what we conclude is, if in most cases rho equal to 0, rho greater than 0, then this is strictly positive, and hence variance of beta hat is underestimated in this formula. So the variance of OLS estimators are underestimated in the presence of autocorrelation problem. So that is the second consequence of the presence of autocorrelation. In consequent to this, the standard errors are underestimated and t statistics are actually inflated or overestimated. So this also has got the problem in the inference of the regression model. In the presence of autocorrelation, R square is equal to 1 minus sigma Et square divided by 1 minus rho square sigma Yt square. For any rho greater than 0, we can very easily conclude that this term really is overestimated when rho is the absolute value of rho is greater than 0, otherwise when there is the presence of autocorrelation. So R square is overestimated because of the presence of autocorrelation problem. And similarly, we may define f in terms of R square, that is by n minus k divided by k minus 1. So R squared divided by 1 minus R squared will give you the f ratio. This f is also overestimated if R square is overestimated. And lastly, the interval estimates are also inefficient because this is how the interval estimates are defined: beta hat plus or minus t into standard error beta hat. This defines the interval estimate for beta hat, and similarly we can have the forecasting for each of the values. The interval estimates for the forecasted values are defined as ya hat plus t into standard error of ya hat. So both the things are overestimate. Actually, this the intervals are stretched because of the overestimation of standard error. Now let us see the sources of autocorrelation problem. There are varieties of reasons why the error term in a regression model is autocorrelated. Let us list them. First, the inertia. A special feature of most economic time series, namely GDP, price indices, production, employment, unemployment, is inertia. All these variables move together. The successive observations are likely to be interdependent in all these cases. Secondly, misspecification. Excluded variables become part of the error term and so would cause temporal dependency of error terms. Incorrect functional form. Error due to misspecification of function may also cause dependency among the error terms. Thirdly, the Cobb phenomena. For instance, the supply of many agricultural commodities reflects the Cobb phenomena, where supply reacts to price with a lag of one time period. The farmer's decision on planting of crops influenced by the price prevailing last year. Hence, error in decision would be corrected in the subsequent period, and hence UT cannot be expected to be random. The fourth reason is lags. In an autoregression models, there is most likely that you have the autocorrelation problem. The errors will be autocorrelated. Next, the manipulation of data or smoothing techniques are also the causes for the autocorrelation problem. Most published time series involve some kind of smoothing which do an average out of true disturbances over successive periods to get rid of the seasonal effects in a series. It may cause successive values UT related. The another reason for the autocorrelation problem is models with transformed data. The error terms in the models with transformed variables show a tendency for autocorrelation. For instance, the models of delta yt on delta xt instead of y on x, the equation in growth form, that is log difference as the dependent variable, may also have the tendency in those models the error terms will have some interdependency across time. Then we can also reason out the autocorrelation problem is due to the misspecification of the true random error. The successive values of ut may be related due to purely random factors such as wars, drought, changes in taste, which have an effect over successive periods. In such a case, the true pattern of ut value will really be misspecified. This may be called true autocorrelation, since the root cause of the autoregressiveness lies in the nature of the error term itself. Random effects of one period systematically affects the subsequent period. So this is also a cause for autocorrelation problem. Another reason for the autocorrelation problem is the non-stationarity. In a time series model, if xt and yt are non-stationary, then ut may also be non-stationary. In such case, ut may show a tendency for autocorrelation. So these are all the reasons for the autocorrelation problem. This is knowing these sources is very essential for curing or remedying the autocorrelation problem. Now let us summarize what we have studied so far. In this module, we started off with the meaning of autocorrelation problem, then we proceeded on to the consequences of autocorrelation problem, then we finally saw the sources of autocorrelation problem. In the succeeding module, we are going to see the various tests used to identify the autocorrelation problem and the remedies for the autocorrelation problem. We'll see in the next module. Thank you.